Now we want to expand out and talk a little bit about the context of what it means for reactions to exist at equilibrium. So one of the ways that we can characterize how a reaction will shift, and namely based on you've mixed some reactants and products, what direction will they change? How will their concentrations change based on the system evolving to equilibrium? We can calculate what's called the reaction quotient, or QC. And you will note the formula for QC looks exactly the same as the formula for KC. It's the concentrations in molarity of my products divided by my reactants, where we use the reaction coefficients as exponents. The thing about my reaction quotient Q is it characterizes any conditions, right? You can mix anything you want and you can put those concentrations in here, and QC will characterize what is that kind of balance between reactants and products right now. K, the equilibrium constant, is describing what will happen at equilibrium. So QC describes what does it look like right now. K is describing what it will look like at equilibrium. Because they have very similar formats, even though we normally write them in the exact same way, there are really these kind of equilibrium subscripts in the K equation. Really, those are the concentrations at equilibrium. And so the whole point of having this very, very similar format is that Q numerically is going to relate. We can figure out what's going to happen based on its relationship to Kc. So if Q is less than Kc, okay, if Q is less than Kc, these are fractions, right? So if it's too small, that means the bottom is big, right? So when Q is less than Kc, that means the bottom of my fraction in my QC. Right now, there are too many reactants. And so what that means is that those reactants are going to react and become products. And so we would expect to see a shift to products, because that would be a shift to increasing the top of the fraction, right? So what that would mean is that the concentration of products will increase and the concentration of reactants will be decreasing. Okay, so over as this system evolves to reaching equilibrium. If instead we have that QC is greater than Kc, our system right now, that means there's too many products. There are more products in our mixture than there would be at equilibrium, so the reverse reaction will be faster. The shift will be to reactants, because we're going to make these increase the value of things on the denominator. You're going to make reactants as you move to equilibrium, and there will be less products at equilibrium than the current situation, which you're looking at right now. So QC lets us predict what direction the shift will be, and the direction of the shift informs how those concentrations are going to change. Consider the following reaction. 2NO2 plus 7H2 becomes 2NH3 and 4H2O. So suppose a mixture is prepared with all reactants and products at 0.5 molar. If Kc equals 623, will the concentration of NH3 increase or decrease?
All right, so we want to know, is this concentration of NH3 going to increase or decrease? And so we have made a mixture. We've mixed everything together, and we know that those concentrations are going to change when the system reaches equilibrium. As it's going to evolve, it's going to change your relative amounts. You're going to reach equilibrium. We want to know, is the concentration of NO3 going to increase or decrease when that happens? So we can see that NH3 is a product. So in order for the concentration of NH3 to increase, that would mean it would be a shift to the product side. Whereas a decrease would be a shift to reactants. Right? Because we'd be moving away from the product side, we would be consuming that product and creating reactants. So a shift to reactants there. And so what we want to be able to do then, in order to figure out what's going to happen, is we can compute this QC. And so QC, we know that the functional form is identical to KC, where we put products like NH3 squared H2O. These are all, you'll note everything is a gas, so everything shows up to the fourth bar. Seventh power. And so everything's at 0.5, so just plug them all in. QC is a dynamic value. QC can have any value based on just what's going on, what the mixture of reactants and products is. Everything is at 0.5 molar. So we can just go ahead and put all of them in. And then we're just going to get a number for QC. It's not like Kc, where it has a constant value for that temperature. It's just anything you want. And so QC is equal to 8. And so this tells me that based on this mixture that I have, put everything in at what, 0.5 molar, the relative combination based on this form is 8. Well, we can see if that is less than the Kc value. So QC is less than Kc. And what that means, if we look at this, QC is a fraction. And what we're saying is that this number is too small. At equilibrium, these concentrations would combine to give you a value of 623. Currently, you're at 8. This means as you go to equilibrium, these concentrations will change such that the top of the fraction increases in value and the bottom of the fraction decreases in value. That means this would be a shift. Did I write correctly? Shift to products. Shift to products, so the concentration of NH3 is going to increase. It'll be a shift. NH3 will increase, H2O will increase, H2 will decrease, NO2 will decrease. These concentrations will go down because the more forward reaction will happen. You'll make more product by consuming reactants.
Participation 215, question 3. Consider the following reaction. 2NO2 gas plus 7H2 gas becomes 2NH3 gas and 4H2O gas. Suppose a mixture is prepared with all reactants and products at 2.0 molar. If Kc equals 623, will the concentration of NH3 increase or decrease? This is the third question on participation 215 due Tuesday, February 15th at 11:55 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, consider the following reaction. 2NO2 gas plus 7H2 gas gives you 2NH3 gas and 4H2O gas. Suppose a mixture is prepared with all reactants and products at 2.0 molar. If Kc equals 623, will the concentration of NH3 increase or decrease? Three questions on participation 215. You want to find all those questions, get them all answered, get them submitted by Tuesday night. Got the midweek homework due Wednesday over on Chem 101. We'll do the chemical equilibrium lab, see some fun, see shifts in equilibrium. We'll see how things shift, how things change. And then the second set of videos, end of the week homework, and post lab. If you have any questions also about your test 1 grade, do not hesitate to reach out. Otherwise, that's going to do it for the set of videos. Participation answers will pop up Thursday night. Otherwise, see you in lab, where I will pass back your paper tests, and later in the second set of videos. Take it easy. Bye-bye.